Thank you very much, Richard, and thank you for having me here. One of the perils of being the last speaker at a meeting like this, apart from the fact that maybe my audience has been somewhat depleted by the demands of tea and other things, is that you'll find yourself hearing some things that you think you've heard before. So not to say anything against the excellent organisation of that meeting, but if you ask 5 people to give talks on climate, data and science, the chances are there'll be some similar topics that come up and in all of their talks, and they'll talk about the same thing in different ways. You can think of it as, if you will, as an ensemble of different speakers addressing the same sort of topic. If you find any distinction between the way in which I describe a climate model and the way in which Doug did, for example, then please feel free not to point it out. Thank you. So what I'm going to do today is tell you about 2 things. I'm going to tell you about climate modelling as well, because that's something that's really important where I come from at the Met Office in the UK, where I'm working, as Richard said, on something called UKESM. And UKESM is going to be involved in CMIP6. There's lots of acronyms in that sentence, and I'm going to be unpicking those for you in the course of this talk. If I'm saying anything to you you don't like, or you don't believe, or you don't understand, then, like Doug, please feel free to sing out and ask me a question as we go. I've come a long way to be here with you today, all the way from Exeter. Got up at 5:30 this morning to be with you. So I really want to make sure that my time here is spent with the best use possible. So what I'm going to be talking to you initially is about how we model the climate. And I'll draw a distinction for you between 2 sorts of climate model, a physical climate model and an Earth system model. The Earth system model is the sort of thing that I'm working on, but I'll tell you about the physical climate models as well. And then I'll tell you about a big application, a current application of climate models, which is the Coupled Model Intercomparison Project. You've heard CMIP being bandied around a lot. You thought that the M had something to do with modelling, and you thought the P had something to do with project, and you thought that the C had something to do with climate. No, it's for the Coupled Model Intercomparison Project. I'll talk about its aims and the requirements, the way in which that's set out, and the latest round of the CMIP project, which is CMIP6. And then I'll spend some time telling you about what we're doing about CMIP6 here in the UK, in terms of the models that we're using, and that'll have something to do with the models I told you about in the first part there, those physical and Earth system models that we're developing. And then I'll tell you a little bit about the work we're doing in actually processing the output. We've heard a lot about how the output from CMIP6 is going to be analysed for climate projections and stuff like that. I'm going to be telling you something there about the nitty-gritty, about getting the results out of the models and transforming them into a form that analysts can use all over the world. So, climate modelling. This is my starting point, which is the observation from Coldplay many years ago now, before some of you were born, that we live in a beautiful world. And I'd agree that we do live in a beautiful world. We'd like to keep it that way. Unfortunately, as far as we're concerned, it's not only beautiful, but it's complicated as well. And when you want to build a model of the world, you have to take into account, as Doug has said, lots of different processes. So to build a climate model, you're trying to build a model of the whole world. How do we analyse that? Well, the ancients used to think that the world was only made up of 4 elements. They thought it was fire, water, earth, and air. And we've moved on a little bit since that time. We realise the world is more complicated than that, but not very much. So if you look at the way in which we can model the world, and we think about it in those categorisations in terms of fire, we want to look at modelling processes for the sunlight and heat on the surface of the earth, volcanoes, wildfire. The water is the oceans and the rivers and the ice in different forms. The earth is the vegetation and the soil and the land use, and the air is all the stuff that's happening above the ground, the atmosphere, clouds, aerosols, and the atmospheric chemistry and stuff like that. So these are all the processes that are taking place in the Earth that we have to somehow incorporate in our climate model. And these things don't exist in isolation. So if I highlight for you the way in which moisture from clouds falls as rain, turns into rivers, flows into oceans, gets evaporated back into atmosphere and comes back to clouds, you'll realise there that I've highlighted for you the water cycle. So this is an interaction between the different components in a cyclical form. This is an example of this is the water cycle. Later on we'll talk about the carbon cycle and other cycles that we need to incorporate into our model in order to make it realistic. Again, you've heard this already. You probably know more about this than I do by now. But if you're thinking of those processes that we want to model in our model of the Earth, you think, well, those are the same things that are responsible for the weather, the day-to-day pattern in the atmosphere, the hour-to-hour patterns in the atmosphere outside there. And let me draw my distinction here between weather and climate. As Doug has said already, weather is a short-term thing existing over the course of a few days. Climate is long-term. You can think of climate being the long-term average of our daily weather. The difference in terms of the model you might think of is that the weather forecasting relies on initial conditions. So we look at what's happening right now in terms of observations. We feed those into the model using a simulation, and we project the model forward in time over a period of a few days in order to project what the weather forecast is going to be. Using the initial period, that initial starting condition is no good at all for doing climate modelling, where you're going to be looking at the period of hundreds of years. Whatever we think the climate is going to be in 100 years' time, it won't matter a bean what the weather was today. That's got nothing to do with it because that gets evaporated in terms of the way in which the data gets mixed up in the model. In fact, what the climate modelling a climate model relies on boundary conditions which constrain its behaviour. And typically there we're looking at things like the amount of energy coming into the system from the sun, the amount that's radiated back into Earth or absorbed or reflected by the land surface or the ocean. And these boundary conditions, as again you already know by now, which change the climate, are referred to as forcings. And we're going to be looking at different sorts of forcings when we look at different sorts of climate model. The sorts of questions you can answer, again, with a climate model is to run it forward into the future with prescribed scenarios, typically of atmospheric greenhouse gas concentrations or something like that. So we can do various sets of simulations. These come from CMIP6 that look at the way in which the global average surface temperature will be expected to change under two scenarios. One where carbon dioxide concentrations increase and temperatures rise accordingly, and one where carbon dioxide concentrations are somehow held or reduced, and which, according to the models, temperature starts to stabilise and may even go down. And we can look at different aspects, different outputs from the model, and their effect, their behaviour under these different scenarios. So another one that we might be interested in is the Arctic sea ice extent, which comes down to zero more quickly in a scenario where there are increasing amounts of greenhouse gas than it does in a scenario where they're not. So these are the sorts of questions. These are why climate models are useful, because we can make projections about what's going to happen to the climate, what's going to happen to the Earth in the future by doing simulations using them. In terms of the evolutions of climate models, they've been around for quite a while. And as time has gone on and people have become more and more aware of the different processes that they'd like to have in their model, more of those processes that are mentioned on that initial slide of the Earth, air, fire and water thing. As time has gone on, people have put in more and more, they've started with the atmosphere and then put in more and more processes, land, ocean, sea ice, different sorts of atmospheric chemistry. We've got some carbon cycles here and dynamic vegetation, atmospheric chemistry, all sorts of things going on until we're about here in terms of the complexity of the climate model that we're doing. We're trying to put more processes in, perhaps, to investigate scientific questions that are of interest to us in the way in which we're building the model as well. So that leads us to make a distinction between what I'd call a physical model, where there's a limited set of, if you like, essential processes that are accounted for in the model: radiation, convection, clouds, currents, heat transfer, and these are forced by greenhouse gas concentrations. So this is called a physical model with physical processes are placed there. And what I'm calling an Earth system model, where we have all of these things plus an interactive carbon cycle, which is important because with an interactive carbon cycle, instead of specifying concentrations of things like carbon dioxide and greenhouse gases, we can specify emissions. So we can say how much the atmosphere is taking up into carbon dioxide, how much is going into the ocean, how much is going into the land. We can specify these things in the model, and this is more realistic in terms of monitoring the climate, because it corresponds more closely to real-world observations. So the difference between a physical model and an Earth system model, in my book, is that a physical model is driven by concentrations, and an Earth system model is driven by emissions. We'll come back to that distinction when I look at specific examples of the models we're talking about.
Do you mean, for example,
Yeah.
as emissions?
Yes, yes, yes. So carbon dioxide and other greenhouse gases as well.
But the force by greenhouse gas emissions still means that the human component is not interactive and has feedbacks.
Well, you could run a scenario where we could say, let's pretend the amount that's being emitted by the Earth into the atmosphere is this value, so that we could specify what the emissions are, rather than saying, oh, somehow or other, the concentration in the atmosphere ended up at this value. The point about this is that it allows for interaction between, if there's this much going into the atmosphere, if there's this much being absorbed by the ocean, then we can work out the concentrations that way.
Okay.
So specifying emissions between sources and sinks is something that's more realistic, something that we've got a better handle over in terms of real observations.
Right.
But it means more computation, which I'll come on to. Okay. Okay, so I've said a bit about modelling the climate. I'll tell you something now about the Coupled Model Into Comparison project, CMIP, its aims and requirements, and tell you something about CMIP6, which is the latest round of this project. So CMIP is a project run by the World Climate Research Programme, and it aims to prove our ability to simulate climate phenomena and future climate change. And the idea here is that we use models from climate centres all around the world. So the UK is developing a model, the US is developing several models, Germany's developing climate models, Japan's developing climate models. Each of these models is put through the same set of experiments, and the results are generated and then put together in the same place for people to compare. So the idea here is that you can compare the results of the same model, of different models doing the same experiment to assess the model's strengths and weaknesses. You can collate all those models together into multi-model ensemble, and the way in which this gets used is, for example, in the assessment report of climate science by the Intergovernmental Panel on Climate Change, the IPCC report. This is the thing that every 4 or 5 years or so comes out and makes big headlines in the newspapers. So the input to the assessment report from the IPCC is the results from the latest CMIP. So CMIP6 will be used in the next assessment report from the IPCC, which makes it a big deal. So CMIP6 is the latest round of CMIP. It's the 5th round of CMIP. Don't ask me how they lost count. It began 2 years ago. It runs to the end of 2020. And it's got specific science drivers, better understanding of response to forcing, model biases, predictability and stuff like that. It has, to say the least, a more distributed structure than previous rounds of CMIP. It's more complicated, there are more experiments, and they're generating more data. We'll see why in a minute. So what does it consist of? Well, if you want to enter your model in CMIP6, the first thing you have to do is to use it to run a small set of fundamental experiments. So an atmosphere-only simulation, a pre-industrial control one for about 500 years, so you can get some sort of baseline for the behaviour of the model. A simulation where the amount of CO2 in the atmosphere increases by 1% over year. A simulation where there's an abrupt 4 times CO2 increase, and a historical simulation using specified forcings from CMIP6. So this collection of experiments is called the deck, and it's supposed to be remaining consistent between rounds. We don't know whether it will remain consistent between rounds, because this is the first time they've tried to do something like this.
What's the round?
The next round of CMIP will be CMIP7. And this is something that they've laid down. This is something a new idea for CMIP6. So the aspiration is that it will remain consistent between, and the aspiration then is it provides continuity between within CMIP. So in 1,000 years' time, when we're doing CMIP 999, we'll still be doing these experiments, and our models will.
Can you briefly just say why it's so hard to get the community simply to run their models under the same set of conditions? I mean, in a biochemistry lab, if you're doing things, this would be obvious to people. What's the hurdle here?
Right. It's not. It's not impossible to get them to do that. It's difficult. Do you want me to say any more, or do you want me to be political? Brian? Yeah, pick up discussion. There we are. There we are. I mean, the idea. This isn't the law. This isn't laid down, but it's you could think of it as a suggestion. Say, hey, let's get all the climate models together and run the same set of experiments, and let's see what happens. And for the most part, we're pleased to be able to take part because it's an inspiration, or it's a driver for building new versions of the model to see, well, let's try and put this in and see if that improves its performance. And we're testing it against other climate models in the community. It also means that the results of the model get used in a high-profile, important set of experiments that then get used by the IPCC, for example. I'm sorry if that's a fuzzy answer to the question.
That's okay.
Okay, thank you. Thank you. So this is the entry card for your model. If you want to have a model taking part in CMIP6, you must run these simulations to characterize its performance, because otherwise its other results won't be eligible for inclusion. The second part of CMIP6 is separate model intercomparison projects. So the idea here is that after you've done the central set of experiments, you could pick and choose which projects you'd like to do. And these are projects that are to do with different aspects of climate science, aerosol chemistry, geological science, paleontological performance, different stuff like that. The idea is that you're supposed to pick and choose which experiments you'd like to run. Apparently in the UK we decided not to pick and choose which experiments we'd like to run. We decided we're going to do all of them, so it's just more work for the people who have to organise this thing. There's some various elements of standardisation, coordination, infrastructure and documentation associated with CMIP6 as well. Yeah, there's a picture here. So this is supposed to implement the structure of CMIP6. So this is the DEC experiments down here, the historical simulation. And then these are the various different MIPs around the edge here that look at different aspects of climate science. So they're specialised into doing certain sets of experiments, for example, on decadal prediction, ocean, regional phenomena, clouds and circulation, stuff like that. I'm not going to go into a lot of detail other than to say this is what the structure of CMIP6 is. And then this next picture is supposed to indicate the way in which this is a continuous ribbon through history into the future for future versions of CMIP. So it doesn't matter what the structure of these things is going to be, these experiments in the core of CMIP6 in CMIP will remain the same from CMIP to CMIP. That's the aspiration anyway. Who knows if that'll come to pass. So all these details of the experiments, the things they must do, are laid down in detail. The duration of the runs, the specification of the forcing data, and the way in which this is implemented is via a mechanism called ESDoc. These are tools to support climate model documentation. And so I'll show you a little example of that here. So you go to the ESDoc page. It's got a list of all the different MIPs there, which you can't read, but I'm telling you it's a list of all the different MIPs there. I click on one of them. This is the CMIP6 DEC runs, and it consists of various different experiments. You can't read those either, so I'll click on one of those and say this is the PI control, the pre-industrial control that must last for 500 years to give some sort of baseline performance for the model. And the complete specifications of what the experiment ought to be are laid out on this page. Things like temporal constraints, it must be 500 years long, ensemble requirements, if any, the model configuration you need, and the forcing constraint. So this specifies what the experiment is that you're supposed to be running with your model. CMIP6 also specifies the duration of the experiments for the different MIPs. There's great variation there between the different MIPs and within the MIPs, the priorities, the tiers for the different runs that they are electing to take part in.
What are the units across?
These are years.
Years.
Yeah, model years. Not well, they might be real years at the rate we're going. So. Yeah, sorry, these are model years. A big one. Yeah. So all of the details of the experiments are laid out, including the list of the variables to be calculated during the course of the runs and submitted. This is known as a data request. It's collated from the specifications from all the MIPs, or each MIP has decided, well, we'd like to do some experiments and aerosol chemistry. We'd like the model to be producing these variables and these frequencies on these grids, and we'd like those to be specified in this way. That information gets put into the data request, and it's used when you're doing the model run to set it up and to do the post-processing. It also specifies the format and the content of the results. So each model produces its output in its own output format. CMIP6, when you put that out into the model world, into the real world, is not interested in the format of your model's output. It wants it all in some standardized format, as Brian was alluding to earlier on. And so I'll talk about the way in which we're taking the output from our models and converting it into something to that standard form that CMIP6 wants to have. So as I said, it needs to be converted into a standard format. This conversion software has to be developed by the modelling centres themselves, because each model is different. They can't make that standard as well. There is some software from the community, the Climate Model Output Rewriter Library, which has been provided, or CMOR. That's very helpful. Each file needs to be carefully labelled with metadata to specify which model it's been run on, which institution did the running, what experiment it came from, stuff like that. We'll see some examples about that later on. And then this data, once it's produced, needs to be submitted to the Earth System Grid Federation, the ESGF, which we've heard a lot about already. This is a repository for all the data from CMIP6, for all the runs from all the models. And it will, as I said, it'll be used for climate scientists and future analysis. And the UK node is run by CEDA, the Centre for Environmental Data Analysis. That is your new name, isn't it, Brian, rather than well, new in climate terms, in paleo terms. Yeah.
Quick question, just.
Yeah, sure.
In CMIP5 and in every round before, I think all the models were run at different spatial resolutions. Is that going to be standardized as well, or is that?
No, you're free to choose the resolution that you want, because there's a diversification of sorts of models. So some models will be Earth system models, some which will go slower than physical models, for example. And so you're free to choose which resolution you want.
Right?
No, that's space.
That's space.
That's space.
Some models actually have totally different grids.
Yeah, that's a pain
So
in the neck.
it'd be unfair to.
Yeah, but there's
Right, your next question will be, are we going to regrid all the output to be a common grid?
Or is that what the climate model output rewrite does?
No, it does not. It does not. All it does is it sticks the labels on there. So it says, Jeremy did this on Thursday, and he used this model, and he was trying to contribute to this experiment. It doesn't mess around with the resolution of the data in that way. Discussions have taken place about, gee, wouldn't it be great if everybody was on the same grid? Brian?
Well, those are the discussions that we've been this morning. There are some reasons why you want to do it.
Yeah.
There are lots of reasons why you wouldn't. We can take them in the discussions with them.
Thank you. Thank you. Right. So that's the idea. That's the idea of CMIP. Now, let me tell you what we're doing in this country, in the UK. Models to be used. So who's doing CMIP? Well, we all are, really. National Environment Centre for Research Council, UK Academia, the Met Office, plus some people who aren't even in the UK. Some of our international partners, KMA in Korea, NIWA in New Zealand, they are contributing to CMIP6 in the UK using our models. They're helping us with that. As I said, UK, although it's a small, vibrant country, is punching above its weight in terms of climate science, because it's decided it wants to contribute to all the MIPs, which is lovely. Some of the MIP leads are actually in the UK. In terms of the increasing complexity of this thing compared to previous rounds, it is estimated, and Brian may correct me here, that we will be contributing about 5 petabytes of data to CMIP6. You're hoping that number's 3. Some low integer here of petabytes is just the contribution from the UK. By contrast, in the previous rounds, everybody, every country, every model, every experiment took up 1.5 petabytes. So that gives you some idea of the increased complexity and onus on storage, onus on processing that we have this time around.
Will that 3 to 5 petabytes stay in the UK?
No,
And
no.
then be federated?
Yeah, sorry, yes. So initially it gets sorry, a big one. Initially it gets submitted to the UK node of ESGF, which is run by Brian's team at CEDA, and then that's federated in some sense by ESGF, such that for the data analyst, he can sit at some terminal in the way in which Amy described and say, well, I want this from the UK run, I want that from the German run, and effectively he shouldn't care where it's really coming from. I mean, it might take a while for it all to be assembled, but that's not one of the details that he knows. So once we've got it onto CEDA, then it can go to the whole world.
And is Brian's shop next door to the supercomputers, or will there have to be some
No,
transfer?
I'll come on to that.
Okay.
I'll come on to that. These are the models we're using in CMIP6 in the UK. Remember I said there's a physical model and an Earth system model. The physical model comes at you in two flavours depending on its resolution. So the HAGM3 G3.1 is a catchy name for the physical climate model. It comes in two resolutions, N96 Orca 1, N216 Orca 025. I'll show you what those mean in a second. And then there's one Earth system configuration, UKESM 1, which consists of this physical climate model, the low resolution climate model, plus a whole load of other stuff that the scientists have decided to put in order to slow it down. I mean, to make it more interesting in terms of climate science. This is run at the same resolution as the low resolution version of the physical climate model. We have this snazzy picture here to indicate the effects of changing resolution. So this is the N96, the low resolution version of the atmosphere, 130 kilometre grid boxes at the equator. This is N216, the high resolution version of the atmosphere, 60 kilometre grid boxes. And this is N1024, 12 kilometre resolution grid boxes at the equator. This one is not being used, I'm not talking about it here, but it's used in the special MIP called high-res MIP. And again, that's been done in collaboration with our friends at the University of Reading, mostly done by NERC. So, you can stare at that and say, well, yeah, I can see the low resolution one is blocky and the high resolution one is smooth. Woohoo. Similarly for the ocean, this is 1 degree. This is the low resolution version of our model. 1/4 degree, that's the higher resolution. 1/12 degree, that's the even higher resolution version of the model. So we developed these models, got them working, put them out there to the MIPS and said, hey, MIPS, choose which one you want to use. Choose which model is most appropriate to answer the scientific questions you're interested in. And this is the way in which it got divided up. And again, there's not a lot of detail in here because I'm not going to tell you what these MIPS are doing. There's a lot of people, however, that are interested in using the UK Earth system model because that is more useful for the scientific questions they are concerned with. I mentioned already that CMIP6 has got more experiments and variables than CMIP5. Some people think it's about a 6-fold increase in terms of the number of data sets, in terms of the variables and the experiments they got. When they specify this list of things that we want you to output from your model, in the olden days they distributed an Excel spreadsheet, which I've already seen the word yuck attached to in a presentation today. I wonder if you can remember where that came from. Excel is last year's thing. So this is being distributed using a version-controlled XML document, which makes it more interrogable, and with an API for navigating that data request in programs, for example. So what we did with this thing as soon as we got it, we turned it into a spreadsheet so we could use it. There's about 2,000 variables, each with about 20 attributes. And we receive this thing, and we have to decide if our model is going to be in CMIP, we're going to run it. But for each of these variables, does our model already produce it? Does it already produce the average atmosphere temperature, for example? Well, I hope it probably does. Does it already produce this really cool variable that somebody from atmospheric chemistry has just come up? Well, maybe it doesn't, but perhaps we can put new code into the model to make it produce this variable. Could we produce this variable by post-processing other outputs from the model to produce it? Perhaps we could do that. So we had to assess the data request in that way. The data request is a moving target, so every now and again we had to redo this, but we're getting closer to fulfillment there. So this is what the data request looks like. Lists of interesting variables, near surface air temperature, cloud fraction, precipitation, all the usual things you'd expect a climate model to produce. When we interrogate it, we want to walk up to it to say, what variables has this MIP requested? Because information about what variable gets requested by and which MIP is included in the data request. Which MIPs, or conversely, if I look at a variable, which MIPs would like this variable? What would be the impact if we decided we couldn't produce the surface temperature? Which MIPs would be cross with us if we ran the model and didn't have a value of the temperature for our model? Well, probably all of them. So we'd probably better do that. And then, I'm not going to go into this detail. We developed a language for interrogating this data request, which allows for different sorts of questions, finds variables for the current process, and configures the filters to extract the appropriate data from the archive. And it's based on the API that the data request comes with us. So we do the runs, and each component of the model, the atmosphere or the ice or the ocean or the atmospheric chemistry or the ocean biogeochemistry, outputs several variables. Each variable is spatially and temporally sampled. When the model runs, it writes its output to disk, and that gets immediately archived to tape. And what the model is producing may not align with what the MIPS want it to produce, in order to take part in the experiment. So what we have to do is we have to process the model variables to create the MIP requested variables. So to find out what those variables are, we go back to the data request. We obtain the variable list for each experiment using our interrogation application. So the way in which we produce the requested variables is to combine the details from the data request. We take the description of the model capabilities, including things like whether or not the model can actually produce this variable, which MIPs are we producing to, or which, if there's only one MIP that requests this variable and it would be really hard to produce it, can we just say we're not going to produce it? We have to take all those sorts of decisions ourselves. Also, how much data will be generated. If one MIP wants every temperature value on a very fine grid every minute of the day for 500 years, do we really want to produce that from our model, or can we just not say we're going to do that? We make the requested variables list, JSON file, which is used to drive our climate data dissemination system. This is what it looks like. Over here, we've got our model running with some produce of the model variables that get written to tape. We've got information about the model capabilities, some practical considerations, i.e. how much do we want to produce these variables. This gets combined with the data request and its interface to produce this thing called a requested variable list. And then this is the climate data dissemination system here. I'll say more about this in a second. First of all, we extract the model output. We configure the conversion process. We do the conversion. And then in this final step, we take the converted data files and transfer them back to our archive. So we've got a copy of that. And we also notify CEDA that they're available for copy to ESGF. So all of this stuff here, in response to your question, happens inside the building, inside the Met Office. This step here happens down the road in Oxfordshire. So you know where Exeter is. Well, you'll know where Exeter is tomorrow. Oxfordshire is some way away. This is in Oxfordshire. This is all in Exeter. So, which I think answered your question there.
Yeah. It's about the same distance between NCAR and the place you're
Yeah.
Okay.
Yeah. It's peanuts in American terms, but yeah.
Okay. So I guess is the transfer by fiber optics, or is it by a truck?
At the moment, it's by cable. Yeah.
It's fibre optics. It's also worth knowing there's also simulations being run in Edinburgh as well.
Yeah.
So,
Yes. Yeah. So most of this work is being done on the machines at Exeter, but there are other locations where they get it done as well. And not all of this stuff gets produced at the same time. We don't suddenly phone up Brian and say, hey, we've got 5 petabytes of data. Can you have it on there by this evening? We're going to get it done in stages. Let me just go into that in a bit more detail. We've got this climate data dissemination system, Python-based, to manage the extraction of the model output from the archive, configuring the conversion package, converting it for a given MIP, and then transfer that output data to SGF. And it works in conjunction with this internal database that we've developed to monitor and control the processing stage. So this extraction step uses the requested variables list. So we pull out the output from the model output that we need and place it in storage on a batch processing cluster, because doing this conversion, although it's tedious, is something that's easily parallelized. So we run these we run the conversion step in parallel in a way in which I'll show you in a second. We've got this configuration step which sets up the conversion application, specifying which MIP variable names we want to produce. Then we have the conversion step itself to create the MIP variables, the variables that we want to actually put up on the ESGF from the model output. We combine the model variables together. We might we need to have some sort of mapping that says this thing that was produced by the model, it corresponds to this thing that this MIP wants, or this thing and this thing that was produced by the model, combine them together to make this, and that produces that variable that the model wants. Multiple variables are converted in parallel. The variables get saved in NetCDF files. You've heard NetCDF as being a wonderful thing. We think it's a wonderful thing too. It's written in a special format, the CF climate format, which is a standard, using CMOR and the MIP table information. And then finally we transfer the data to ESGF. So the way in which we do this step is we put the converted data back in the tape archive, and then we send a message to CEDA, and at their leisure they can extract those files from our tape archive for them. So it's a pull request that they put through. Let me just I'm nearly finished. Let me tell you something about the way in which to do this conversion, because this is the bottleneck, if you like, for this conversion, to go from the stuff that's produced by the model to the stuff that the CMIP6 actually wants. The model output is large. What do I mean by that? We ran our low-resolution physical model for 10 years and produced 3.2 terabytes of data. Now, some of that is not needed. Some of that is stuff that the model produces anyway, but it gives you some sort of idea of the size of the data sets we're playing with. Again, this is the low-resolution physical model. The high-resolution physical model will produce more data in 10 years, and the Earth system model would also produce more data in 10 years, because the Earth system model has got more processes and it does more output. It outputs more interesting variables. The way in which our model is set up is it outputs variables. It doesn't do all its output into a single big file, because we do not like having 3.2 terabyte files lying around on our disk. That's kind of dirty. So we output into several files depending on the frequency. So if it's a daily data, or is it 3-hourly data, or is it monthly data, they go into different files depending on their frequency. Depending on what component they're coming from, and they're coming from the atmosphere or the aerosol or from the ocean. And these output streams are chunked in time. So there's not one big file lasting for 10 years. They could be, say, well, let's have the first year, let's have the second year, or let's have the first month, let's have the second month, let's have the third month, to optimize the file sizes. So all of this means we've got several files of output that come out from the model, which means that the conversion of the data in the files can be done in parallel. So this is a picture, a schematic, if you like, of the way in which we're doing some of this output, part of it. With a setup step, this is the conversion of the atmospheric physics part of one component of the model for starting in 1850. This is the conversion of the same data starting in 1855. So this converts the first 5 years. This converts the second 5 years. These two steps here draw the results together, put them together, produce the finalized version for the end of that 10-year period. They get organized, they get concatenated, and they get sent out back to tape storage. The important thing is that this and this are the time-dependent steps, and they can be run at the same time. So they're run in parallel, because we're running this on a batch processing cluster. It might not look like we're getting much speed up there, but if we scale it to something like that, all of those boxes in red are all running at the same time. So we're parallelizing, converting multiple versions of the files, multiple data sets, multiple variables at the same time, which makes it more efficient. The way in which we do this is using internally developed software. ROSE is a framework for running, managing meteorological suites, and Silk is a task scheduling engine. And in fact, this is the output from ROSE and Silk that's been used to produce these pictures here. So we do all this, we do all the conversion, and we finally end up with a data file. Now, I'm going to do something very unusual here. You've been hearing about science data and climate data and stuff like that. I'm actually going to show you a climate data file. Nobody's ever done that before. And this is an example of it. And this specifies, it's an illustration of the sorts of things that comes from the CMIP6 specification. So this comes in various, this is the file up at the top there, and the different parts of this file name are laid down by CMIP6. It must have this format. So it starts with a variable name for some sort of control vocabulary used in the data request. In this case, TA is the air temperature. The next part is the MIP table, which is how the variables are organised. In this case, AMON means a monthly atmospheric data. The next thing is the model name that's actually used to produce this data. We've got HADGEM3 GC 3.1 minus LL. You see that's been truncated and simplified compared to what we called it originally, and that's because CMIP6 thought that if we put the full name in, then this name will be out here somewhere. So we had to use LL for low resolution atmosphere, low resolution ocean. The next thing is the experiment name. So you produce this variable. What experiment were you running with the model? In this case, it's the pre-industrial control. There's some sort of variant label here which specifies, is this from a run on this experiment that comes from an ensemble? We've been talking about ensemble. There are different ways in which to set up the ensemble for realization, initialization, physics, or forcing, different ways, different indices for which member of the ensemble are we talking about here. We've got a grid label here which specifies the native resolution for the grid. And finally, we've got some duration. You produce this variable. When did it start? When did it finish? All of this, we're producing thousands of files like this, and we're uploading them to CMIP6. And they're produced in this form so that in 20 years' time, after I've gone mad and left the Met Office because running CMIP6 was too much for me, somebody can walk up to this file and still get some idea of what's inside it. And there's metadata inside the header of the file as well. So what we're doing is, at the moment, is implementing some quality control. Well, what we're doing is we've started the runs. We started the deck runs using our models. Setting these things up is not straightforward. We've got them running, and we have the experiments running on our internal Met Office machine at the moment. We're putting in some procedures for quality controlling the MIP variables using a compliance checker, which checks the compliance of the net CDF files against the CF conventions that were mentioned by Brian earlier on. We've extended this to CMIP6. We do this check after we've done the conversion, and the reason we do that is so we do the check before we submit it or before we ask CEDA to upload the file, because we know that CEDA are going to be checking this anyway, so we might as well do the check ourselves. We do some housekeeping, we're doing some interfacing with the ESDoc, and we're doing some testing of this data conversion system that I've been telling you about here. So, what I've told you is that CMIP6 is a major application for climate models. It's more complicated than previous rounds, as I think I've endeavoured to make clear. There's more experiments, there's more data, there's more options, more all sorts of things going on. We've been inspired by this complication to develop improvements for the way in which we set up the model, the way in which we interrogate the data request, and the way in which we process the output. The model still gets run in the same way, but the way in which it gets set up and the way in which the output gets processed, we've improved. We've responded to the complexity involved in CMIP6 by building new systems, using parallel processing where possible, and automating standard working practices. Thank you. That's all I have to say. I appreciate your attention. I'll be happy to take any questions now. Thank you.